Okay, I actually have expanded this a little bit. I don't know whether we can get the light off here, off the screen. You might try. Well, of course, the two guys that made it all possible once they got there, on the backs of over 400,000 others, they were Armstrong and Aldrin. And I've expanded this a little bit to include some other issues. But let's start with the samples. 21.8 kilograms. Mare basalts are old. That was one of the first things. Harold Urey predicted they would be old. All my colleagues at the USGS thought they would be somewhat younger. And indeed, they were old, and that meant the early solar system history was recorded on the moon. Very, very important for understanding the early history of the Earth, of course. First billion years, extremely violent. Complex organic molecules were organized simultaneously. Have to keep that in mind. That is on Earth and probably on Mars. Water-rich regolith would alter to clay, and therefore clay may have been the templates for the organization of those organic molecules. Again, both on the Earth and Mars. For some reason it doesn't want to, can somebody back there advance? I don't know why it's not, there we go. Now, the Mare basalt units were diverse in chemistry, age, and mineralogy. Probably more so than most of us thought they would be. There were 5 basalt cooling units apparently sampled. That may represent West Crater stratigraphy. We'll mention that again in a moment. 9 separate vesicle assemblages, which I still don't understand, even though I documented them in the introduction of the first lunar science volume. Probably represent unique flows and or interflow differentiation with respect to the volatile content as well as the temperature and pressure of the flows themselves. There were 2 varieties of pyroclastic glasses identified. And again, I'll mention that again in a moment. Right here, the sampling area, and note that it's essentially on a ray from West Crater. And therefore, we may have seen stratigraphy that West Crater impacted. And also, this dark area may be the source of the pyroclastic volatiles, a la the Shorty crater at Apollo 17. At least it is anomalous. And it would be, I'll just mention here and may mention again, be nice if we took some of those, if we could really look inside some of the Apollo 11 volcanic beads, glasses, and see if we can't see some of those olivine-associated water indications. I don't know that anybody's ever done that. We probably ought to do that. Now, the magma ocean fractional crystallization and remelting hypothesis originated because of the identification by 2 teams, Wood and Smith's teams, of anorthositic fragments in the regolith. There was a differentiated source, obviously, for the basalt relative to the overall moon, specific titanium-rich source or assimilation region. And the vesicles indicate, to me at least, that hydrogen was present in that source region. And that in turn strongly suggests, I think, that water once was present in the source region, but had probably been largely decomposed by the exsolution of immiscible iron sulfur liquid that ended up giving you hydrogen, as well as FeO, additional FeO. I suspect that if we really start to go back and look at the Apollo 11 samples, we'll identify that there was a creep component, now that we know that there was creep, there is a creep component in the moon. And also, I mentioned already the water detection in the pyroclastics. I just think it'd be an interesting exercise for somebody to see if we can identify water in some of those pyroclastic glasses. The mineralogy, 6 new titanium-bearing minerals, if I remember correctly, 3 of which I guess now have been found on Earth, but we didn't know about until we went to the moon. Low defect crystallization of the minerals, presumably because of the 1/6 gravity environment. Isotopic geochemistry, quite extensive understanding of that, or beginning of an understanding of that, including that the moon is as old as the solar system. Now, 100084 sample, very, very important from the standpoint of understanding the solar wind volatile resources in the regolith. We have hydrogen, helium, nitrogen, and carbon in particular, and their isotopes. Heating of that regolith produces a fair amount of H2O. Our estimates at Wisconsin some time ago were that about a third of the hydrogen will come off as water if you heat to about 700 degrees C. You don't want to go much higher than that or you'll start to produce some sulfuric acid probably by the decomposition of FES. And in fact, I'm becoming more and more suspicious that that may be a problem even at lower temperatures. 50% probably losses due to agitation. When you compare the 100084 with the concentration of solar wind volatiles in regolith breccias that Neil also sampled. So we had both basalt and regolith breccias in the sample collection. Of course, I can't not mention that helium-3 fusion fuel is present in that at a concentration, if you account for agitation, probably at about 20 parts per billion. Lunar settlement, Mars expedition consumables, of course, are represented by these solar wind volatiles. Now, lunar surface operations, that's what I've expanded this into a little bit. The regolith, really what we learned from Apollo 11 confirmed what we already knew from the Surveyor landings. People tend to forget that, particularly in media reports, that we knew the limb wasn't going to sink out of sight because Surveyor didn't sink out of sight. And there was high initial bearing strength, moderate cohesion, electrostatic bonding of particles. This is all disrupted by traffic fairly easily, so that's something that has to be considered in the long term of how do you stabilize surfaces that are going to be subjected to high traffic. It's incompressible. This basically closest packing, as you might expect from something that's been tamped for hundreds of millions of years, or at least tens of millions of years. Traditional coring and drilling resisted. We never quite got that right, even all the way through Apollo 17. We improved the coring and drilling techniques, but in the end, it was very, very difficult to get cores out of the regolith, and we talked about that at a league meeting some years ago. Dust, about 50% is less than 60 microns, about 1% less than 1 micron, and that's the unusual part of the dust on the moon. That's what we have to use engineering solutions to try to prevent getting into the habitats. In fact, I had a little bit of an allergic reaction to that dust. It went away over the course of the 3 days on the moon, but there was a flight surgeon removing suits from the command module that had such a reaction he could not continue. And so it is a physiological issue, but I don't think we ought to get panicked about it because there are engineering solutions to keeping that dust out of habitats. And in the final analysis, it's magnetic, and you can use electromagnetic filters. This maturation by solar wind sputtering and micrometeor impacts produces agglutinates and nanophase iron. There's, as I indicated, a layered defense required against those effects, but I think that's pretty straightforward. Industrial materials and elements are present in the regolith for the long term. Centering of the regolith is almost certainly reasonable to consider. Some forms of concrete as well, and additive manufacturing of specialized materials is something that we can now consider in the future. All of this comes from looking at 100084 in some detail. The experimental data that has come from the two experiments that, three experiments actually, that were deployed, a solar wind gathering experiment that Johannes Geist put together, the seismometer, and the retroreflector. Solar wind composition, very high seismic Q of the crust equals a dry megaregolith. It meant that the moon rang like a bell when hit. Thermal insulation, because of that megaregolith, allowed the Mare magma generation to take place. Low seismic noise from the lunar interior, although later on we found it wasn't totally quiet. And the high precision Earth-Moon distance through laser ranging gave us some lunar motion dynamics and a opportunity to understand the lunar core, both at its presence and its size. And we actually have three independent sources of information ultimately about the core. With that, I'd ask for any additions to this list that you might have. Thank you very much.
Questions? Please use the microphones.
Just one comment. You know this, and most of the people in the room know this, but there are a few who do not. The iconic picture of Neil Armstrong's footprint that you showed on one of your slides as a background is actually a civil engineering experiment. Dave Carrier talked to Neil before launch and urged him to take a picture of his footprint, that one, because it gave soil mechanics experts a lot of information about the angle of repose and the cohesion and the depth of penetration of the regolith. And while people see it as a symbolic thing, it actually was an experiment.
Yeah, it actually shows the angle of internal friction, which I've never fully understood. But from that, we, in other future or later geotechnical analyses, we can probably know that the digging into the lunar surface can be supported down to about 3 meters by a wall, which is important from a mining point of view.
Dan Britt, University of Central Florida. Interesting as always. Can you say a few more words about the effect of high traffic on the surface material, and how much did the disaggregation eventually bottom out, or did it get worse over time?
No, it will, as near as I can tell, traffic will continually stir up to deeper and deeper depths. It breaks through some of the cohesive bonding. It's these are unsatisfied electron bonds that are holding things together, and you're just going to have to deal with it in some way. Now, I think again, there's an engineering solution. Sure. The original macadam was a Scottish gravel, in a sense, roadway, and once you're producing various resources on the moon, you're also going to have the capability to divert a certain size fraction of gravel that you might have in order to stabilize these surfaces. So again, I don't think it's a big issue. Larry Taylor at one time proposed that we try to microwave these surfaces. I think that is going to take some experimentation to see if indeed you can build a stable microwave center that won't also break up and eventually cause you difficulties. I tend to favor a macadam of some kind. No, yes.
Were there, Jack Lissauer, NASA Ames, was any of the Apollo 11 return sample analyzed to show dates of dust or other small pieces of highlands being much older than the Maria?
I'll defer to someone in the crowd. I think that there were attempts to date various individual fragments. We certainly had the dates on the Mare themselves. I don't know that anybody came up with a date on the anorthosite fragments or not. Does anybody know? No answer. But again, if we never got back to the moon, you can imagine the level of concentration on these samples that would have taken place. And a lot of the things we found out later probably would have been deciphered, particularly with the advance of analytical technology that we have today. I mean, that's one reason why the Apollo missions never ended for those of us in the room and many others, because of the advance of analytical technology, as well as the advance of ideas. And that's going to happen indefinitely. I see no reason why Apollo ever stops for at least the scientific community.
Last two questions. Jake Bleacher, NASA. Dan's question about understanding maybe some of the geotechnical properties and how they would be impacted by longer-term activities on the surface. I was just wondering what you think might be the or several of the most important issues for us to think about if we want to have a sustained presence on the lunar surface. What do we need to tackle, and what measurements could we make between now and 2024 in order to prepare for that?
One of the big decisions, I think, is going to be whether you build your habitats with a water shell around them or whether you use a thicker shell of regolith. And I can't tell you which is going to provide the better protection against solar radiation, solar proton and radiation, and galactic cosmic rays. But long-term habitation on the moon is going to have to protect against both of those, and it may be a combination. It may be both of them will be used. But that's an issue that is going to take some thought and probably some in situ experimentation to really see. The thing you have to remember is the in situ properties of the regolith are very different than what we get in the samples that we have and what is produced by simulants. That regolith has been created in a 10 to the minus 12 torr vacuum that is subject to tremendous radiation over long periods of time, primarily from the sun, but also by galactic radiation. So that's something we can't really simulate easily here on Earth, if at all. And we're going to have to do in situ experimentation, I think, to fully understand the geotechnical characteristics of the lunar regolith.
Zakni Honeybee, you mentioned that even after 3 missions, we didn't get drilling done right. Could you elaborate what happened on 15, 16, 17, and how would you improve it?
Well, on Apollo 17, the reason we started coring was because Shoemaker and his team, early field geology team, believed that the lunar regolith would provide us a history of the sun. And we even had core tubes on Apollo 17. I don't think they penetrated more than 4 or 5 inches because of the incompressibility of the surface and the bad design of the core tube. We used a terrestrial design of a core tube and with a flange on it, and that was a mistake. We finally got the drive tube technology pretty well. On Apollo 17 and earlier missions, 16 and 15, we had thin-walled, larger diameter drive tubes. And you could drive those down with some effort down. We did to 70 centimeters and get good cores. The drill cores, though, the deep drill cores, it took a while to finally get the flutes meshed on each core so that you could remove the cuttings. But by having those flutes on the outside, that meant that when you tried to pull it out, you would get rotation of fragments into the flutes, and since, again, the regolith is incompressible, that took a heck of a lot of effort to actually get the cores out. And so some of the work that you've been doing, Chris, on pneumatic removal of cuttings and having smooth wall drill pieces is, I think, very important. That may be the answer, is the pneumatic approach. But we really, even with 17, even though we got a nearly complete 3-meter core, it was not easy to do. And we need a lot of cores if we really believe that we're going to understand the history of the sun. And I do now, as I mentioned in my Mazursky lecture earlier this year, I think we're now figuring out how to do that. At least with the Apollo 17 core, which is nearly complete. But we need more of those, and we need to be deeper. We need to get down into the deepest portions of the regolith and get a good solid cores and start to look at the variation in isotopic chemistry that comes with those cores.
Thank you.
Thank you.